Assalamualaikum and hi guys, this is 7.1 part 2. So today we are going to continue learning on acids and bases. Here are the learning outcomes. At the end of this lesson, students should be able to define strong acid and base, weak acid and base, pH, pOH and pKw. But in this video we are going to focus on acid and bases first, and we are going to continue with this definition in the next lecture. How to determine the strength of acids and bases. Right. We generally classify acids and bases as either strong or weak according to the extent of their dissociation into ions in water. Right. So we are going to focus on the dissociation equation. Strong acid. What's meant by strong acid? Strong acid dissociate completely or 100% into ions in water. Therefore, the alpha value is equal to 1.0, which is the maximum value. What's meant by alpha? Alpha means degree of dissociation. In this lecture, since we are dealing with calculation of pH value for strong acid only, so we are not going to focus on alpha value too much. But don't worry, you are going to encounter alpha later on during your tutorial session. Right? Consider the general equation of dissociation of an acid, strong acid. So we have an acid here, Ha aqueous, react with water, produces H3O plus aqueous plus A minus aqueous. So this is an acid, right? Because it loses its proton, forming A minus. So this is acid, while here in this case water react as a base because it's going to accept H plus forming H3O plus. So now please focus on this arrow, reaction arrow. Okay, you can see that it is using the single-headed arrow that represent the complete dissociation of acid into its ion. Okay. So when a strong acid react with water, it dissociates completely into its ion, which is H3O plus aqueous and also A minus aqueous. When HA react completely with water, that means after the reaction ended, there are no more HA remains in the reacting vessel. That means at the end of the reaction, the species that are available in our reacting vessel is just the ions, H2O plus ions and A minus ions. Got it? Right? So whenever you are writing the dissociation equation, or we can say when a strong acid react with water, it react completely. So please write down the equation by using the fully headed arrow or single-headed arrow here. Okay, when it react completely, that makes Ka value extremely large. What's meant by Ka? Ka stand for acid dissociation constant. Acid dissociation constant. Okay. The larger the Ka value, okay, that's mean the stronger the acid. For example, we have HNO3. Okay, aqueous. This is an example of a strong acid, which is nitric acid. React with water, completely dissociate, right? Single-headed arrow into ions. When this acid loses its proton, it's going to form its conjugate base, which is NO3 minus aqueous, while this water react as a base because it accepts proton, okay, forming H2O plus aqueous. That means at the end of the reaction, there are no more acids in the reacting vessel, just left with our ions. Okay, you need to memorize the strong acid in our syllabus. Okay, the easiest one is going to be the hydrohalic acid. Hydrohalic acid means hydrogen, okay, plus halogen. Halogen is group 17, right? But not all hydrohalic acid are strong acids. Right here we have HCl. Okay, Cl is the second member of group 17, and then we have bromine, the third member, and also we have iodine. So we have HCl, HBr, and HI. How about HF? No, HF is a weak acid, right? HF is a weak acid. Next, another example is going to be commonly used oxo acids such as HNO3, nitric acid, H2SO4, we have sulfuric acid, and also HClO4, which is called perchloric acid. Perchloric acid. Okay, so there are no other way. You need to memorize that these are the examples of strong acid that you are going to encounter in SK015. Next, weak acid. Weak acid dissociate very slightly into ions in water. Therefore, the alpha value is going to be less than 1. Okay, so how to write down the dissociation equation for a weak acid? Let's say we have Ha here. Okay, this is example of weak acid. Okay, this is weak acid. When reacting with water, it's going to dissociate into its ion. But then, why do we write the reaction arrow as the double-headed arrow? Because it represents that the dissociation occur very slightly. That means it do not completely dissociate. So whenever you are writing the dissociation equation for a weak acid, please make sure you are using this kind of arrow. We call it double-headed arrow. Right. So now, okay, this acid loses its proton, okay, forming its conjugate base A minus, and and water in this case react as a base where it accepts H plus, forming H3O plus equals. So when we say HA, which represent the weak acid, dissociate very slightly. That means it do not react completely. So at the end of the reaction, what are the species remain in the reacting vessel? Do we have any HA left? Okay, nay? Yes, because HA do not react completely or do not dissociate completely. Therefore, at the end of the reaction, there are still HA or weak acid remaining in the reacting vessel, right? Of course, plus its ions. Okay. Therefore, the Ka value is very small. Remember, Ka stands for acid dissociation constant. The larger the Ka value, the stronger the acid. So that means the smaller the Ka value, the weaker the acid. For example, we have HCN here. Okay. HCN is an example of weak acid. When react with water, dissociate partially into its ion. So we have HCN losing its proton, okay, forms Cn minus, whereas H2O react as a base, accept proton, forming H2O plus. Because HCN is a weak acid, therefore, when writing the dissociation equation of HCN, we need to use the double-headed arrow. Right, so far so good. Okay, of course, the first one is hydrohalic acid, which is HF. Yeah, because previously we already learned that HF is not a strong acid. So that means it is a weak acid. Next, we have oxo acids. Another example of oxo acids are HClO, HNO2, and also H3PO4. Right? And then an organic acid. Okay, we usually have this one. right? Carboxylic acid, COOH. So you can, whenever you see the COOH, that stands for the carboxylic acid, or also known as organic acid. Another example are HCN, like we just did just now, and also H2S. Strong base. So strong base dissociate completely, 100% into ions in water, of course, because the word strong. Remember, strong acid or strong base are going to dissociate completely. Therefore, the Kb value is extremely large. What's meant by Kb? Kb means base dissociation constant. Okay, usually strong bases are made up of soluble compounds containing O2 minus or OH minus ions. For example, right, we have M2O or MOH. That's mean M is metal, group 1. Okay, group 1 metal, such as lithium, sodium, potassium, rubidium, and cesium. Or we also have formula of MO or MOH2. That's mean M stand for group 2 metal, such as calcium, strontium, and barium. The equation for strong base. Group 1. Example given is sodium. So sodium oxide react with water, completely dissociate into its ion, which is Na plus aqueous plus OH minus aqueous. So don't forget to balance the equation. So 2 mole sodium here, 2 mole sodium, 2 mole oxygen, 2 mole hydrogen. And then check on the charge, 0, 0, plus 2, minus 2, sum up equal to 0. So this is the correct dissociation equation for sodium hydroxide. Next we have sodium oxide. Next we have sodium hydroxide, dissociate completely, forming its ion Na plus aqueous and also OH minus aqueous. Next we move on to group 2. Example given is calcium. So let's say we have calcium oxide, react with water, dissociate completely into Ca2 plus aqueous and OH minus aqueous. Don't forget to balance the charge. Calcium is already balanced. Don't forget to balance the equation. Calcium is already balanced. Next, we have 2 more of oxygen and hydrogen on the left side. Now we have 2 times by 2. Check on the charge. Yes, already balanced. Next, we have calcium hydroxide. Dissociate completely into calcium Ca2 plus OH minus. Next, don't forget to balance here. Right? So this is the correct dissociation equation for calcium hydroxide. Next, weak base. Weak base dissociate very slightly into ions in water. Therefore, the base dissociation constant or Kb is very small. For example, molecule with an nitrogen atom that has lone pair electrons. For example, ammonia. Okay, so it got lone pair here. Right? So how to write the dissociation equation for ammonia? Okay, so when ammonia react with water, it's going to dissociate partially. Okay, dissociate partially because it is a weak base. Therefore, we need to use the double-headed arrow. So ammonia react as a base, so base is going to accept proton, okay, forming NH4+, and in this case, water is going to be the acid, so it loses its proton forming H minus ions. Right? So far so good. Exercise. Right, so classify each of the following compounds as strong acid, weak acid, strong base or weak base, or species with negligible acidity. So now let's make a guess. Okay, give you some time, okay, to look at the equation given and try to guess by yourself. Okay, what does these compounds represent? Here is the answer. Right, so we have this compound. So we can say that it consists of COOH. As I said earlier, COOH means carboxylic acid. Carboxylic acid is an organic acid. So is it a strong or weak acid? It is a weak acid. Right. So next we have KOH. So hydroxide. Hydroxide plus the metal. K is group 1 metal. So it is a weak base or strong base. Yes, strong base. Next we have this molecule, and then we can see nitrogen there. Okay, we can see nitrogen there. Okay, and this nitrogen actually got one lone pair. So this is a weak base. Next we have HNO2. Right? HNO2 is a weak acid. H2SO4 sulfuric acid is a strong acid. Next we have HPO4 2 minus. This is a weak acid. Then we have CH4 methane. Here methane is neither acid or base. Okay, we can it is a species with negligible acidity. Then last one we have CH3 and H3 plus. So even though it consists of nitrogen here, but this nitrogen got no lone pair. But then it has a positive charge. That means it has an extra proton here. So it is an acid, but it is a weak acid.